All right, so let's talk about this first one. You're just writing a method, right? You're not actually doing the math. What do you think? GCF, A equals 1, A is greater than 1, none. Anybody have any ideas for this one? Or guesses? So you don't know. Maybe logical guess. I like GCF for this one. What can I divide all three of those numbers by? 3. So think about what happens if you divide them all by 3. Then you have x squared plus 4x minus 8. What does a equal? That first term is now 1. So this one is a GCF that leads to the a equals 1 method. All right, let's look at the next one. It's a binomial. What is the only thing I can write for a binomial? GCF. If it's 2 terms, the only thing it could be is a GCF. All right, what about the next one? Andrew? Very good. There is a GCF here. 10, 6, and 2 are all even numbers. And if they're all even numbers, every even number divides by what? So I can divide out a 2. Now, the first number is negative, so it's actually going to be a negative 2 that I can divide out. And when I do that, I get 5x squared, negative divided by a negative, positive 3x. 2 divided by negative 2 is negative 1. A equals 5. And that's greater than 1. So this is a GCF to an A is greater than 1. Number 4 is a binomial, so it could only be GCF. They're both even, so there's at least a GCF of 2. All right, what about number 5? What does A equal? 1, right? That first term is 1. It's a trinomial. A equals 1, A equals 1. 3 terms. First term is x squared. No number in front. What about number 7? It's 2 terms, so I'm thinking GCF, but it's not. Because this is a 1, and that is an 81. The only thing 1 and 81 have in common is 1. 1's not a GCF. And this has an x and that doesn't have an x, so it doesn't have a GCF that way either. This one would be none. Right? In order to be GCF, it has to have a GCF, and this pair does not. What about 8? Another none. Think of things that multiply to 16. 1, 4, and 16. None of those numbers go into 25 except 1. And they don't both have a variable, so this is another none. All right, what about number 9? They're not all even, so I can't divide out a 2. A is greater than 1. My initial reaction would be, let me see if I can get rid of this 2. But that's a decimal, and so I can't get rid of the 2, so this one's A is greater than 1. Number 10 is also A is greater than 1. I can't get rid of that 9 to make it A equals 1. Not all of these numbers will divide by 9, right? And they don't all have something in common. I can't divide a 4 out of them. I can't divide a 3 out of all of them because 16 doesn't go into 3. Can't divide a 2 out of them because 9 doesn't go into 2. So there's no GCF here. It's just A is greater than 1. What about number 11? Is there a GCF between 2, 4, and 16? Yeah, they're all even. So I can do a GCF. And if I do that GCF, I get x squared plus 4x minus 8. What does A equal? 1. So this is a GCF to an A equals 1. Number 12 is a binomial, so I'm thinking maybe it could be a GCF. Is there a GCF between 6 and 150? There is. What can I divide out between both of those? Definitely a 3 at least, right? Because 15 goes into 3, so it's, I know it definitely is at least 3. So there is a GCF here. As opposed to down here when there wasn't one. Okay, so I'm just looking at those numbers. If you're not sure, math, arrow to the right 9. 6, 150. I know I told you didn't need your calculators, but I guess a quick check wouldn't hurt, right? 6, they both divide into 6, so there is a GCF. Okay, next one, -12, -38, -20. Is there a GCF there? Is there something that I can divide all of them out by? They're all even, so I definitely can hit it with 2, right? So we're going to go GCF, and I believe the GCF is 2. And in this case, the first number is negative, so the GCF is negative. And I would end up with 6x squared, the double negative, positive, and then the double negative. So it's GCF 2, A is greater than 1 because A is 6. What about number 14? Can I divide anything out of number 14? Is there a common factor between 4, 24, and 36? They're all even, so there definitely is. Okay, so this is a GCF. Now, the common factor is a 4, if you actually check it. And so that means it's going to end up as x squared minus 6x plus 9. A equals 1. What about number 15? Is there a common factor between 5, 25, and 20?
Yes.
Yeah, they all end in 5s or 0s, which means I can divide out a 5. And in this case, I'll divide out a -5 because the first number is negative. I would end up with x squared minus 5x plus 4. So this is a GCF to an A equals 1. Now 16, 12 and 147, I'm not really sure, so I would just do a quick check. It's either GCF or nothing. What was the second number? 147. All right, so they do have a GCF of 3. Anybody have any ideas what we're going to do today? Which of the problems on the board do you think are the fourth method? See the nuns? So today you're going to learn how to factor a binomial when there's no GCF. That's the fourth method. All right, so you'll learn how to factor those, and then we'll be able to factor everything, and we'll be done. And we'll just do a lot of practice this week on our factoring methods. Our test for factoring is on Friday, all right, for Friday of this week. So what we are going to do for these none problems like 7 and 8, well, let's look at them. Anybody see anything that's similar between 7 and 8? Because this new method is very specific. They both have an x squared. Okay, what else? Good. One more thing.
The most subtracting.
All right. So this method is specific to all three of the things you just said. Okay. It's going to be a quadratic. It could also be like a 4th degree, a 6th degree, an 8th degree. The first term needs to have an even exponent, but all the ones we're going to do are quadratics. They're all going to be x squared. Okay. So they need to start with an x squared term. They need to be subtraction, and they need to be perfect squares. The name of the process is called differences, subtraction, of perfect squares. And you'll hear me call it DOPS, differences of perfect squares. So subtraction of perfect squares, okay? It's very specific to that method, or to those numbers. They have to be subtraction. They have to be perfect squares. So let's just do a quick refresh of what our perfect squares are. Now we could technically call 1 a perfect square. 1 times 1 is 1. What's the second perfect square? Not 2. 4. 2 times 2 is 4. 3 times 3, 9. 4 times 4, 16. 5 times 5, 6 times 6, 7 times 7, 8 times 8, 9 times 9, 10 times 10. Gonna stop at 11 times 11, because maybe I can squeeze one more. 12 times 12, and then that list continues, right? So if you're seeing, let's say you're looking at the problem and you're seeing a 20 in the problem, you can't do differences of perfect squares because 20 is not a perfect square. If you're looking at the problem and you have a binomial, it's two numbers, and one of the numbers is 8, you can't do this because 8 is not a perfect square. Coefficients in the perfect squares both have to be perfect squares. If one's a perfect square and one's not, it doesn't work, okay? So it's very specific to these numbers. If you're not seeing one of these numbers, you can't do differences of perfect squares, all right? So in your toolkit, we're going to fill in the last type of factoring, which is section 4, special cases, differences of two squares or differences of perfect squares. Some teachers call it DOTS, differences of two squares. Some teachers call it DOPS, differences of perfect squares. All right, so when you do this, here is how you will factor it. I just have this written in red. You can write this in your notes, you don't have to. But the factored form of this always looks the same. The first number in the first parentheses is going to be the square root of the first term plus the square root of the second term. So the first set of parentheses is the square root of the first plus square root of the second. The second set of parentheses is square root of the first minus square root of the second. So you're going to take the square root of both terms and you're going to use those numbers in both sets of parentheses. One set will get a plus, one set will get a minus. And lucky for you, we just spent a whole unit taking square roots of numbers, right? Well, actually, we were doing third, fourth, fifth roots, right? But you're just going to stick to square roots for this one. So if I want to factor problem 6, it is called differences of perfect squares because it's two terms. The first term has the x squared we talked about. The middle has the minus we talked about. And 9 is a perfect square. So I can do this. When I want to factor this, I am going to take the square root of both of these things. Now you'll notice I'm not putting the minus in. I can't put a minus inside of a square root. Now, last unit we learned that if there's not a number on the outside, what's technically out there? 2. For a square root, when you square something, it's a 2. So a lot of times last unit we had 3s out there and 4s out there. But when nothing was out there, you can imagine that it's a little 2. And the way that you do simplifying a variable is you do the inside number divided by the outside number. Okay? And if you get a whole number, then you just do that division. So inside number 2 divided by outside number 2 is 1, right? So the square root of x squared is just x. You don't need to write the 1. What's the square root of 9? If you don't know, you can type it in your calculator. Second x squared, 9. Square root of 9 is 3. Once you take the square root of both numbers, here's what it does in factored form for dots. You make two sets of parentheses. One set has a plus, one set has a minus. It doesn't matter if the first set has a plus or the first set has the minus. It doesn't matter, okay? Now, these numbers are going to go in the first set and the second set. You're repeating the square root numbers twice. So it's x plus 3, x minus 3. I'm just taking the numbers I square rooted and putting them in both set of parentheses. Every perfect squares factoring has the same format. It's the same numbers in both parentheses. One's a plus, one's a minus. You can check this by redistributing. X times x. X times x is x squared. X times negative 3 is negative 3x. 3 times x is 3x. 3 times negative 3 is negative 9. And when you combine a negative 3 and a positive 3, they cancel out. That's one way to check it. That's just checking it by hand. The other way to check it would be to go to your y equals screen. X squared minus 9. X plus 3. x minus 3. This is the faster way, I think. And just make sure your tables match. So all of the same checking techniques that we had before. But this right here is called factored form. This is my solution. We can only do this when there are two terms. It's got to be a binomial. It's a subtraction problem. It can't be addition. And both terms are perfect squares. And we talked about our perfect squares being 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, and so on. All right, so we're paying specific attention to those numbers. So when I look at example B, I've got x squared. That's a perfect square because any even exponent is a perfect square. And then 100 is a perfect square as well. So now that I know that they're both perfect squares, I'm going to take the square root of each. When you're taking a square root, there's a little 2 out there. So we're doing inside number 2 divided by outside number 2. 2 divided by 2 is 1. We just can't forget that there's an x on that. And the square root of 100 is 10. So once I have the square root of each of those numbers, they go into my factored form. Factored form always looks the same. It's got 2 sets of parentheses, one with a plus, one with a minus. Doesn't matter which one's which. And then my perfect squares, my x and my 10, just go into both of them. And that's factored form. Right, so it really just comes down to taking square roots. We okay with that one? All right, let's look at letter C. 2 terms, binomial, subtraction. 16 is a perfect square, 81 is a perfect square. This is a perfect candidate for DOPS, differences of perfect squares. It's subtraction of 2 perfect squares. So I'm going to take the square root of each. Now you might remember from last unit that to do this, we separated them to separate the mindset. Some of you won't have to do that, right? But it might be helpful for you just to make the connection to the last unit. So the square root of 16 is 4, and 2 goes into 2 one time. I just can't forget about the x. So altogether, the square root of 16x squared is 4x. And the square root of 81 is 9. So I have the square root of each term. When I do differences of perfect squares, one parenthesis gets a plus and the other gets a minus. I'm going to take the 4x and the 9 and put those in both sets of parentheses. So this one was a little different in that the first term had a perfect square too. So it wasn't just x and x, it was 4x and 4x, which makes sense because 4x times 4x is 16x squared. X and x would have just made x squared. I need a 16. So I'm evenly distributing that 16 to 4 times 4. We okay with that one? Why isn't this differences of perfect squares? 32 is not a perfect square. 8 is not a perfect square. So if it's a binomial and they're not perfect squares, then what method do I have to use? It's got to be GCF, right? So the point of this example is I don't want you to think, oh, it's a binomial, it's DOPS. It's not, okay? It has to be perfect squares and subtraction in order for it to be DOPS, and 32 and 8 are not perfect squares. So let's think GCF here. And I'm going to check the GCF between 32 and 8. So if you forget, just from over the weekend, it's math, arrow to the right 9, of 32 and 8. We can't put the negative. Okay, so that GCF is 8. So I'm going to divide out an 8. Am I going to divide out an 8 or an 8x? Just 8. This second term here has no x. So the GCF has no x. All right, so let's see what happens when we divide out an 8. 32 divided by 8 is 4. That x squared stays. 8 divided by 8 is 1. Everybody okay so far? All right, where's the 8 go? It doesn't disappear. It's a GCF. Where's the GCF go?
In front.
In front. So, all right. Two terms, subtraction, both numbers are perfect squares. 4 is a perfect square, 1 is a perfect square. So this is a GCF to a DOPS. You know how in our warm-up we had GCF to A equals 1. GCF to A is greater than 1. You can have GCF to DOPS too. So GCF, I took out the 8, and then when I took out the 8, I had 2 perfect squares. So from here, I'm going to take the square root of 4x squared and the square root of 1. What's the square root of 4x squared? 2x. Square root of 4 is 2. Square root of x squared is x. So 2x. What's square root of 1? 1. All right, so anytime you do DOPS, it looks the same. One parenthesis gets a plus, the other one gets a minus. Each parentheses get the same numbers. They're each going to get a 2x, and they're each going to get a 1. And don't forget that that GCF is still part of your final answer. It just goes to the front. So this was a GCF to a DOPS.
Shouldn't there be 2 8s?
Nope, just 1. The 8 pulls up to the front, and you're not even touching that until the end. So the 8 isn't impacted by the squaring of anything. Good question, though. You just have to put 1. Are you okay with that? All right. We're going to do some practice with this. So in your workbook on page 30, we've got 6 of them. They're pretty quick because you're just taking square roots. So I'm going to go with 5 minutes. I don't think you'll need 5 minutes, so I'm going to give you 5 minutes anyway. All right? So you're going to take the differences of perfect squares. I believe they are all differences of perfect squares. I think every number you're looking at right now on the board is a perfect square. So you're just going to take the square roots and make sure you can put them in factored form. All right, let's see if we can get 6 different people to give me the answers for these. It's a challenge. All right, 22. All right, Gabe, what do you got? Very good. All right, someone different. Very good. All right, someone different. Good. All right, 3 more. Yeah. Very good. Are we okay on that one? When the coefficient's there, sometimes that one's a little trickier. 4x plus 9, 4x minus 9. All right, that's 4.
5x plus 8 and 5x minus 8.
Very good. All right, last one. We were doing so good. All right, good.
3x plus 40, 3x minus 40.
Very good. Isn't this the easiest of all of them? I feel like this is the easiest. All you have to do is take square roots. The format's the same every time. You don't have to worry about steps. The only thing you have to put into your calculator is the square root if you don't know it already. And a lot of those you probably know off the top of your head. All right, so that is the last factoring method that we're going to learn, which means in terms of new factoring content, we're done. All right, we're going to do a lot of practice this week. So I am going to give you what looks exactly like your quiz, okay? So what it is 10 problems, which I think your quiz is maybe 12. It might be a little longer than this. So your quiz on Friday is similar in that it's got problems, and the problems that you're going to look at are all in standard form, meaning the highest degrees first, the lowest degrees last, and your goal is to put it in factored form. And at this point now, you know 4 different methods of factoring. So the first thing you're going to do is decide what method of factoring you're going to use. And there's a blank. In the blank, you're going to write A equals 1, GCF, A is greater than 1, DOPS, or maybe you're going to write GCF and A equals 1, GCF and A is greater than 1, GCF and DOPS. Get what I mean? And then you're going to actually factor it here. All right? There are going to be a few ways for you to check your work. One, you're going to be with a partner or a group of people. I'm going to let you choose, right? So you can check in with that person. If you have the same answer, chances are that answer is probably right, okay? That's option one. Option two is really quick. Type the original question into Y1 and your answer into Y2. If the table matches, you are 1000% correct, okay? Option three, there is an answer key on Canvas and a video explanation on Canvas. So if you want help, obviously I'm here, I can come help you. Or if you just want to do something quick and you're not sure what you did wrong, you can watch the video or look at the answer key online. So 3 different ways. I don't have a key posted. All right, so it says answer key randomly written on the back border. I don't, okay? So I figured between you and your partner, the Y equals screen and the key on Canvas, you should be fine, all right? So this is the goal for the rest of the class. We're here till 39, all right? So we've got about 20 minutes to factor 10. That's 2 minutes per problem. DOPS problems take like 30 seconds, if that. So then you should have plenty of time to get through all 10. I really want you to make sure you're checking your answers and making sure you're right. Questions for me? If you finish before time's up, you can work on Math Excel. You can finish all of it now. Let me just get all of these out to you. Right? So once you have one, feel free to move anywhere in the room. Work with whoever you want, but just make sure you know how to factor. Factoring is the most important thing you will learn this semester. I want to make sure you guys are good. If you want to work with me, I'm happy to do that too. So you can sit up here, we can do some problems together. Totally your choice.